In this last section, we'll look at some common errors, good practices, as well as applications of UV and visible spectrophotometry. So first, let's take a look at common errors. Common errors in spectrophotometry may arise from the instrument itself, for example, stray light, or it could also be analytical and human-related errors. For example, there may be interferences from other components or the solvent itself that absorbs light at that particular wavelength. So the result will not be accurate because the absorbance is not solely due to the analyte alone. If there is any solid matter that is suspended in the sample, for example, some dust or some excipients that are not soluble, that may also cause scattering of light, which would affect the absorbance. So in order to obtain good, precise, and reproducible results, we must ensure a few things. Firstly, the sample solution must be properly prepared, meaning no weighing errors or volumetric errors or temperature errors or any other human errors when preparing the sample. The compound must also be completely dissolved because insoluble materials cannot be determined by spectrophotometry. The solution has to be clear and not turbid. So if there are any solid particles that are still present in the solution, then it has to be filtered or centrifuged first. There must also not be any air bubbles present on the cuvette window because the air bubbles could interfere with the transmission of light. Ideally, the sample components should also not be adsorbed onto the cuvette walls. This is because if the sample starts coming out of the solution and sticking onto the cuvette walls, the absorbance of the sample will change over time. Cuvettes must be clean and the correct side must be oriented towards the direction of the light beam. For the blank or the reference solvent, it must also be subjected to exactly the same procedure as the sample. We should also aim for the absorbance of the sample to be between 0.1 and 1.5. To avoid stray light from getting into the detector, we must always close the cover of the sample compartment when we are using the spectrophotometer. Spectrophotometers contain mirrors as well as diffraction gratings, which has to be aligned perfectly in order to direct the path of the light correctly. So to avoid these components from shifting around, the spectrophotometer should be placed on a stable bench, which is free from vibration. And we also try not to move the spectrophotometer from place to place. To avoid any interferences with the absorbance, the environment should be clean and dust-free. Spectrophotometers also contain electronic components such as the detector. So to ensure that the electronics are working properly, we need to avoid electrical interference, humidity, as well as temperature variations. The instrument should also not be exposed to direct sunlight, which can heat up the equipment. The instrument should also be calibrated regularly, and any other manufacturer's recommendations should be followed. UV and visible spectrophotometry have several applications in pharmaceutical analysis. The most commonly used application is quantitative determination of active ingredients in formulated drugs. UV and visible spectrophotometry can also be used for qualitative tests to check the identity of a drug. There are also several other uses of UV and visible spectrophotometry, which I will elaborate on later. For quantitative analysis using UV and visible spectrophotometry, pharmacopoeias will usually state the standard A 1% 1 cm value of a drug at a particular wavelength. This value is also known as the specific absorbance. The specific absorbance value is the absorbance of a 1% weight over volume, which is 1 gram in 100 ml solution, measured using a 1 cm path length cuvette. So if we want to know the concentration of a solution, we would first measure its absorbance and then compare this absorbance to the specific absorbance value. So if you remember the Beer-Lambert law, absorbance equals to a constant times the path length of a cuvette times the concentration of the solution. This constant, represented by epsilon, is the molar extinction coefficient, which is the absorbance of a 1 molar solution. We use this equation when the concentration of the solution is in moles per liter. However, in pharmaceutical analysis, we often use percent weight over volume instead of molar to express the concentration of a solution. So we often use this equation instead, where the constant is A 1% 1 cm and the concentration is expressed in grams over 100 ml, which is also equals to percent weight over volume. Now let's try using the Beer-Lambert law to solve a question. Carbimazole has a specific absorbance at 291 nanometers or 557. A solution of carbimazole has a measured absorbance of 0.557 at this same wavelength. What is the concentration of the solution? To try out this question, pause the video, and to check your answer, press play again. Let's take a look at the Beer-Lambert law equation. Absorbance equals to specific absorbance times path length times concentration. The path length B is the path length of the cuvette, and it is always standardized as 1 centimeter. So the value of B is 1. Now if we do a little bit of rearranging of the equation, then to find the concentration, you will take the absorbance of the sample divided by the specific absorbance. So let's sub in the values. Absorbance of the sample is 0.557 and the specific absorbance is 557. So our concentration of the sample is 0.001% weight over volume. Let's try another similar exercise. Isoprenoline has a specific absorbance value of 100 at 280 nanometers. A solution of isoprenoline has a measured absorbance of 0.500 at the same wavelength. What is its concentration? Press pause to try out the calculation on your own, then press play to see the answer. Again, let's use the same equation for the Beer-Lambert law. Remember, B is the path length and the cuvettes are standardized at 1 cm. So rearranging the equation to calculate C, concentration, you need absorbance over the specific absorbance. Let's write that down. Now let's sub in the values. So we get the answer of 0.005% weight over volume. In quantitative analysis using UV and visible absorbance, we need to make a few assumptions. First of all, there are no interfering excipients, meaning that any absorbance of the sample is solely due to the analyte. The sample must also be free of any suspended solid matter that would cause light scattering. Another assumption is that the Beer-Lambert law applies, meaning the absorbance is directly proportional to the concentration. The usual working range for quantitative analysis is usually between 0.1 to 0.8 absorbance. At very high and very low concentrations, negative deviation from the Beer-Lambert law occurs, meaning that the graph is not linear. Therefore, we try to avoid using either very high or very low concentrations. Besides quantitative analysis, UV and visible spectrophotometry can also be used in qualitative analysis to perform identity checks. To check the identity of a compound, we can look at the shape of the UV and visible spectrum, the wavelength of maximum absorbance, the peak intensities, as well as the specific absorbance value. However, UV visible spectrophotometry is not a confirmatory test because solvents and other factors such as pH and temperature can also influence the UV spectrum. Also, other compounds may have similar spectra. Since UV visible spectra do not have sufficient fine structure to confirm the identity of a compound, further confirmatory tests are usually required. This is an example of how we would use the UV visible spectrum of a compound to determine its identity. So from the spectrum of riboflavin shown here, let's record the values of lambda max and absorbance at lambda max. We can see from the UV visible spectrum that there are 4 peaks, so let's identify the wavelengths as well as the absorbance corresponding to the wavelengths. The first peak is at 220 nanometers and the absorbance is about 0.6. The next peak is at 270 nanometers and the absorbance is 0.65. The third peak is at 380 nanometers and the absorbance is lower at 0.2. And the fourth peak here is at wavelength 450 nanometers with an absorbance of 0.25. So if you have an unknown compound which you think might be riboflavin, you can run a UV visible spectrum for that compound and compare the spectrum with that of riboflavin. Finally, let's look at a few other applications of UV and visible spectrophotometry. One is determining partition coefficient. Partition coefficient is determined by shaking a mixture of a drug in organic solvent and water. The organic solvent that's used is octanol. Octanol and water are immiscible, so you will see a layer of octanol on top of a layer of water. The partition coefficient P is the concentration of the drug in octanol divided by the concentration of the drug in water. The value of P indicates how hydrophobic the drug is. A higher P will indicate that the drug is more hydrophobic and therefore it dissolves more in octanol, which is the organic solvent. UV spectrophotometry can be used to determine the concentration of drug in octanol and the concentration of the drug in water. Another use of UV and visible spectrophotometry is to determine the solubility of a drug. So to do this, we shape an excess amount of drug in water or a buffer until we reach equilibrium. Then the solution can be taken and the UV absorbance can be measured. So from there, we can determine the concentration of the drug that has dissolved. UV spectrophotometry can also be used to determine the rate of drug release from a formulation. Let's say we have a tablet, for example, a sustained release tablet, and we want to monitor how much of the drug is released over time. We would put the tablet into a dissolution apparatus. Then at certain intervals of time, we would draw out some of this solution to check how much drug there is in the solution. To check the amount of drug release, we can use UV spectrophotometry to check the concentration of the solution. UV and visible spectrophotometry are easy to use and they are also reasonably cheap because the instruments are not too expensive. The method is also robust, meaning that it can handle slight changes in the method. This method is precise when used to quantify drugs in formulations. UV spectrophotometry is also routinely used to determine some of the physicochemical properties of drugs, such as solubility and partition coefficient. However, the limitation of UV and visible spectrophotometry is that it is only moderately selective, and the selectivity of the method depends on the chromophore. So if peak absorption occurs at a wavelength where many other compounds also absorb at that particular wavelength, then the method will not be very selective. But if the compound is able to absorb at a wavelength where not many other compounds can absorb the light, then it will be a more selective method. UV spectrophotometry is also more suited to analysis of one single analyte and not so much for analysis of mixtures unless it is paired with another method such as liquid chromatography.